Okie dokie. If we are talking about either of these, we are going to need to establish some mathematical ground rules. And that's the language of radians and angular velocities and things like that. So, just to clarify, for those who don't know, a radian, it's an angle. So instead of splitting a full rotation of a circle into 360 degrees, as you probably are used to, the concept behind using radians is instead you're splitting it into 2π pieces. 2π is a number like any other. It's a very specific number, but yeah, you are splitting a full rotation to 2π radians. Why? It is calculated such that when you use radians, 1 radian is the angle formed by a circular arc at the center of a circle when the arc length is equal to its radius. This is not a fantastic drawing of 1 radian because 1 radian is, from memory, roughly equal to 55 or something, 57.3 degrees. So that's roughly what 1 radian looks like. And in my drawing, you can see, look, 1 radian is calculated such that this red length here, if I change my ink color, is exactly equal to my arc length here. It's probably annoying a few of you that I've used ink colors different to displayed here, because S would be this length and R is the radius, and this theta is equal to 1 radian. So when you draw a Trivial Pursuit wedge, and you such that the radius is equal to the arc length, that means you've got yourself 1 radian. And that's the definition. Everything else follows on from that. If you do the maths, you'll find that that means that you can fit 2π radians in 1 full rotation. So if 360 degrees fits in 1 full rotation and that equals 2π radians, that also means 180 degrees is equal to 1π radians. And so if you're converting between them, your conversion factor is 180 over pi. Fab. And obviously, 1 degree is very, very slim, but 1 radian is actually quite chunky. So if you're converting between the two, make sure that if you're converting from radians to degrees, you end up with a bigger number because it's a smaller unit. And if you're converting back the other way, you're going from a smaller unit to a bigger unit. So your number should be smaller. As long as that's in your head, you shouldn't go wrong. We say that an object is periodically traveling at a constant speed in a complete circle if it's going uniform circular motion. Okay, so this is the great tension at the, no pun intended, but that's the great tension at the center of circular motion, is that your speed can be constant. You're traveling around the circle, uniform circular motion, but your velocity is constantly changing. And so your acceleration indicated, so the force, the tension in this string is indicated by the green arrow, but it also indicates the direction of the acceleration. Whereas this purple trajectory is where its displacement and its velocity will be pointing. At a given amount of time, its velocity will be pointing that direction. So if we're spinning a bob, whirling it around our head, hooray, great fun. It's moving at constant speed, but its velocity is always changing. So at one moment, it's got a sort of velocity that's pointing in this direction. Let's call that v1. And then at the next moment, it's pointing this direction, v2. Velocity is a vector. And so you might well ask, well, how did we get from v1 to v2? Well, we must have had a change in velocity. And we have a change in velocity is what acceleration means. And here it is, a little acceleration. It's a vector. And where does it appear on my vector diagram up here? There it is. The acceleration points this direction on my diagram, and lo and behold, it points in the same direction on my vector diagram. Because acceleration is a change in velocity per unit second, or per unit time, that's exactly what's going on. We go from v1 to v2 via this acceleration. Okay. Now, of course, in the next second, well, the acceleration has now changed direction as well as the velocity, and so you're constantly playing this game of cat and mouse around the circle, where the velocity is always changing because the acceleration makes it change, but that means that the acceleration also has to change for the next moment, and so on and so forth. The bob is accelerating. Don't forget that. This is centripetal acceleration. Okay, I said that this part of the course was about establishing a few mathematical ground rules. An important concept to understand is angular displacement. So just as we might talk when we talk about linear motion, we'd talk about regular displacement. We'd say, look, that's it, you've traveled 2 meters in that direction. Angular displacement is the same thing, but it's just talking about how much angle you've traveled through. Okay. So just as you can travel 8 meters or x meters, you can rotate theta radians. Period, hopefully a concept you've met before, indicated by t, is the time to do a complete cycle. Angular speed, again, by analogy to linear motion. In linear motion, you can say, well, okay, you've gone x meters. What if you do x meters per second? That's now velocity. Switch back to your angular analog. Okay, you've rotated omega radians. What about if you rotate omega radians per second? That's angular speed. So it's rather than just a single step in a direction or a single rotation, it's if you're doing those every second, so on. So you're really enacting motion. Radians per second. Fab. Briefly, if the period is the time to take one full revolution, how many revolutions do per second? That's the frequency. It is going to be 1 revolution per period is going to be your frequency. The angular speed then. If you are doing let's say 3 full revolutions per second, how many radians are you turning in per second? Well, you're doing 2 pi and 2 pi and 2 pi. So you're doing 6 pi radians per second. How did we get that calculation? Well, we simply multiplied the frequency by how many radians there are per revolution, 2 pi. So if you're ever given the frequency of circular motion, you can work out the angular speed by simply multiplying it by 2 pi, the amount of radians in 1 revolution. And the definition of this angular speed is a change in angle over a change in time. Instantaneous velocity, v, is the velocity component tangential to the circle in meters per second. Yep. Okay. So far I've been talking about linear motion and angular motion almost separately. So how can we link them? This is why radians come in useful. If I turn 1 radian per second, we defined radians as the angle such that the arc length is equal to the radius. Therefore, however many radians we're turning per second, the angular speed, if we simply multiply that by the radius, that is going to be our linear velocity, our linear speed. Okay, that's not necessarily a derivation, it's just an explanation. But get this equivalence into your head. That is a really useful conversion to be aware of. What are the corollaries of this? Well, we know that omega is 2 pi f, so I could write this as 2 pi fr, which means I could write this as 2 pi r over t. Does that make sense? Yes, it does, actually. If you think about the mathematical format of this, you're saying 2 pi r. Have you seen that before in maths? Yes, we have. That's the circumference of a circle. And so the period is how long it takes to do a full rotation. And I'm saying, however long it takes to do a full rotation, you're going to divide the circumference of that circle by that number. This equation, v equals the circumference over the time it takes to travel the circumference. That's just velocity is equal to distance over time. You know, year 7 maths, but in a circular context. Okay, hopefully that wasn't too confusing. It's important to get a sort of really solid understanding of exactly what's going on with this angular speed and how it relates to linear speed. Okay, let's push on. The Earth orbits the Sun at a distance of approximately 150 million kilometers. Estimate the angular speed and instantaneous velocity of Earth. Okie dokie. We want the angular speed. We're given the radius. And it's 3 marks worth, which is quite generous. Yep. What we really want then is perhaps the period. Do we know the period? Well, yeah, actually we do. From primary school geography, we know how long a year is, and that's how long it takes for the Earth to orbit the Sun. It's 1 year. That's not the most convenient unit. Convert it to seconds. And they've even been assiduous enough to include leap years, 365.25. But they're not including leap centuries, but that's fine. Right, angular speed in terms of period. Yep. So we're interested in working out the angular speed. So we've got it in frequency there. Let's write it in period. We know what the period of the motion of the Earth around the Sun is now. So we've got the angular speed, really. And in fact, we didn't need r to work out the angular speed. It's when we're asked for the instantaneous velocity that we'll now need it, because we have just said that the instantaneous speed is the angular speed times the radius. Okay, so get your answer from the previous part and just multiply it by r. Okay.